recorded. So for the fractional life method, you're still given a pair of data. This time, the data that is given is the initial concentration of the species and the fraction that has been converted, or rather not the fraction, but the time it took for the fraction of the said species to be converted. So that fraction could be 1/3, that could be 1/4. This one, the F that you see here is the final concentration of the species divided by the initial concentration. So the F actually here is not representing the portion that has been converted, but rather the fraction of the entire initial concentration that remained unconverted. So this one is the unconverted portion. We divide it by the initial concentration. And that's the F that you're going to place here. Now you're going to use this data if the problem is giving you the time it took to have this F, the time it took to have this F, and the initial concentration. So in half-life method, what you actually plotted is the initial concentration against the half-life. In here, you're going to plot the initial concentration against the time it took for this F. Okay, now you plot the log of TF. You use the same principle and the same procedure that was discussed in the half-life method versus the log of CaO, or that could be the ln of T sub F versus the ln of CaO. This will give the reaction order just like the half-life method. Now for the half-life method, you have this generalization. Actually, these are generalizations discussed also by the author of our book, Levenspiel, and it's taken from his book. So for n greater than 1, that is for order of reactions greater than 1, fractional conversion increases with increased concentration. So meaning if we're going to increase the initial concentration, it is expected that the amount that is converted or the fraction that is converted increases also. That is for the order of reaction greater than 1. If the order is less than 1, fractional conversion decreases with increased concentration. So even if we increase the concentration, this time your degree of conversion decreases if the order of the reaction is less than 1. Now, what about if the order of the reaction is equal to 1? So this time, the fractional conversion will be independent of the initial concentration. Okay, these are the 3 generalizations that could be made out of the derivation of the fractional life method formula that was presented to you just a while ago. Okay, now we move on. So we go now to multiple reactions. So far we've been looking into single reactions that are happening for a particular time, but one by one. They have to occur one by one, or they don't occur simultaneously, or one reaction is not dependent on another. So with multiple reactions, from the term itself, multiple, meaning we have several reactions to consider. Some are simultaneously happening, others are not simultaneously happening, or has to wait for a particular reaction to happen first prior to the next occurring also, or commencing to occur. Now, the first of these multiple reactions would be the irreversible reaction, which is said to be parallel. Okay, can't show again. So I will show to you the unprojected part. Okay, so for this irreversible reactions in parallel, when we set up the net rate equation for the 2 reactions that are simultaneously happening, we are to consider the reactions, or we are to assume that those reactions are elementary. So in this case, this reaction for the formation of R from A and for the formation of S from A as well happens simultaneously. So we have to write the net rate equation in this manner. So the rate in terms of A, which is also represented by the rate of change of the concentration of A with respect to time, should be equated to K sub 1 C sub A, which is for the first of the two reactions, and K sub 2 C sub A still for the second reaction. Now, since we have C sub A in both terms, we can factor the C sub A, and we have the quantity K sub 1 plus K sub 2 being multiplied to it. This is one equation that could be set up in this parallel reaction or simultaneous reaction. Now, if we will set a rate equation in terms of R only, or in terms of the formation of R, then that would be R sub R being equal to dCr dt, or the rate of formation of R, being equal to the product of K sub R C sub A. This K sub R is different than K sub 1, but in this case, if you recall the kinetics of homogeneous reactions that we have discussed, since stoichiometrically the ratio of of A to R is just 1, so we can automatically say that this K sub R is also equal to K sub 1, which could be K sub A, because they have stoichiometrically the same coefficients. But if not, K sub R is not equal to the K sub 1 that you are seeing here. Now, if you will set up also a rate in terms of product S, so the rate of change of the concentration of S is equal to K sub S C sub A. Now, in all these reactions, in these two reactions specifically, you still have a common concentration, which is C sub A, primarily because we based our rates on the reacting species. Now, let me proceed. Hopefully, everything can be shown now. I don't know. It can't be shown. So in here, it has to be noted that at any particular time, the amount remaining for A, or the concentration of A, the concentration of R, and the concentration of S is a constant. Or rather, the sum of these three concentrations will be a constant. Now, the first equation that was shown to you, that is the net rate of reaction based on species A, will give you a plot with a slope equal to K sub 1 plus K sub 2. The last equation will yield a plot with slope K sub 1 over K sub 2. And solving the two simultaneously, the two equations simultaneously will give you the values of the two rate constants. The equations, again, I have written here, and it cannot be shown. I don't know what's wrong with this. Anyway, that's the unprojected equation. This one came from the first equation that was set up in the previous slide, the net rate of reaction of A. So I'd like to go back to that, so that would be clear to everybody. This one, the net rate of reaction in terms of A. If you're going to process the DE, this will be the equation that you'll be getting. Now, again, going back to this slide, if these two, you take the ratio of, okay, the resulting equation would be this. You cancel the DTs in the DCR and the DCS. They all have DTs. So you cancel those. Now you have the ratio of the rates of formation of R and S, which is also equal to the rate constants in terms of R and S. So this is the one that is being referred to here, that the last equation yields a plot with slope K sub 1 over K sub 2. The slope that is being referred to here is this one. The K sub R and the K sub S is just equal to K sub 1 over K sub 2, because in here in the first slide, the stoichiometric coefficients of A, R, and S are all 1. So if we take the ratio of these two, this will be the resulting equation. Your K sub R and your K sub S is also K sub 1 over K sub 2. From in here, if you're going to look at this, you have two derivatives, but these are all constant. So if you're going to deal with the DE, taking out of the picture the R and the S, let's say, for example, you take this out and you're going to only deal with these two, and you process the differential equation and appropriately write the limits of your integration, then you will have C sub r minus C sub RO from the integral of this all over C sub S minus C sub SO coming from the integral of this being equal to this also, which could also be equated to K sub 1 and K sub 1 over K sub 2. This last statement, which says that if you solve the two equations simultaneously, you'll be getting the value of K sub 1 and K sub 2 came from here. So you have here the ratio of K sub 1 to K sub 2. And if the problem gives you the time for a certain amount to remain or a certain concentration to be reached for C sub 8, then you have another equation for K sub 1 and K sub 2 in here. So if you solve these two equations simultaneously, you'll be able to get the very important K sub 1 and K sub 2 for this parallel reaction, or we call it competing or simultaneous reactions. Okay, so these are the different relationships, the different formulas that you can use when you deal with parallel reactions. Now let's go to Levenspiel and check what particular problem can be solved using this principle that we have just discussed. Okay. Levenspiel is fond of using a natural observable phenomena to compare or use analogy with the principle of kinetics, or where we can apply also the principle of kinetics. So we have this problem regarding beta 100 Bushby. So beta 100 Bushby lives or likes to play the gaming tables for relaxation. He does not expect to win, and he doesn't. So he picks games in which losses are a given small portion or a small fraction of the money bet. Now he plays steadily without a break, and the sizes of his bets are proportional to the money he has. So if he has more money, he will have big bets. If he has small money, he will of course have small bets. And he doesn't take note, he doesn't win, he always loses. If at galloping dominoes, this is just one game he plays, it takes him 4 hours to lose half of his money. And it takes him 2 hours to lose half of his money at chuck a luck. How long can he play both games simultaneously? If he starts with $1,000 and quits when he has $10 left, which is just enough for a quick nip and a car fare home. So he makes sure that he have $10 left because he knows that he's always going to lose. But as long as he has $10 left, he can still eat something and go home. So that's what he does. So you have to understand here that this scenario is when he plays the game individually. So if at galloping dominoes, it takes him 4 hours to lose half of his money, and it takes him 2 hours to lose half of that same money, whatever that money may be amount, at shakalak. This time, how long can he play both games simultaneously? If he has to start with $1,000 and quits when he has $10 left. So that is beta 100 Bushby. He likes to lose, and he always loses, but it doesn't mind as long as he has $10 left. Okay, so let's go to our whiteboard. This is 313. And let's change the color. This is number 3-13. So what's our given set of information regarding the betting pattern of beta 100 Bushby, or BB for short? So let's say, for example, we'll write here in galloping dominoes, this is the game that he plays. the half-life of his money is 4 hours. And chocolate, the half-life is 2 hours. These two games he plays separately in these two scenarios. Now, the problem is asking if now he plays these games together. I don't know how he's going to do that, but he's going to play this game simultaneously. And if he has to start with, let's say the money that he has is CAO, initial money that he has is $1,000, so we'll put it there. You are to find the time. So in here, you are to find the time when CA is just 10. So in this scenario, you have playing simultaneously GD and CL. Okay. His betting pattern is based on his cash at hand. And of course, his losing pattern will also be based on the bets that he makes. So in this case, we can write this particular, shall I say, condition in which he plays as a parallel reaction. So if we have A as his initial money, and this one is for GD, and this one is for chocolate. Okay. The corresponding, let's say, I'll place this as G, and you have here as C. Anyway, any letter here would do, because what is important is he have the representation for the initial money that he has, or for the initial reactant that we're going to compare to the money that he has. If we write this reaction, parallel reaction in terms, or if we write the rate equation for this parallel reaction, that would be then, if I will have this as K sub 1 and this as K sub 2, then we have K sub 1 CA plus K sub 2 still CA. And we can simplify this just like what's shown to you in the slides. You can factor out CA, you have this one. In here, you will have the formula ln of CA over CAO being equal to, so you can place the negative there, being equal to K sub 1 plus K sub 2, and you have T. Okay, just a short derivation of how the first formula came about. So let's say that's our first formula. Now our problem is we still have to determine the two rate constants, or the rate constant, the rates, which is dependent on the rate constants of the way he loses when he plays the game separately. That is the galloping domino and the chocolate. So for galloping dominoes, so for GD, if you set up a rate equation separately for that, and since parallel reaction is to be viewed to be elementary, and this is a reaction that is, of course, have to be represented in this manner because it's elementary, then this is the way it is. And we've learned how to come up with the correct expression for this one in our discussion in the first part of this set of slides. So we have K1T. Now we know that if it's half-life that we're going to place here, this one will be half of this. So I can place 1/2 CAO over CAO is equal to K1 T sub 1/2. If I will now appropriately substitute what I can work on in the problem. So I have negative ln of 1/2 being equal to K sub 1, and this is for galloping dominoes, and it took him 4 hours to lose half of his money. So from here, you'll be getting a K1 value, which is equal to 0.1733. So this is per hour because the time that is provided is per hour or in hours. So for Chak Alak, the same thing. So I will not anymore write this one. Or better, we can also have it like that. But this time you use K sub 2 CA. And you still have ln of CA over CAO. And this becomes K sub 2 T. And I'll have a shortcut here. Negative ln of 1/2 is equal to K sub 1 times the half-life here, which is 2 hours for Chak Alak. So in here, by the way, this is K sub 2. So your K sub 2 this time would be 0.3466. So this is also per hour. Now, if you know both your K sub 1 and K sub 2, you can go back to the equation that was set, that you set in here. Since you already know K sub 1 and K sub 2, and everything will be a substitution. So you have negative ln of, remember that he will quit when he has $10 left and he started with $1,000, and you have to take the values of the case that you have solved initially. So you have 0.1733 plus 0.3466. And this is to be multiplied to, of course, the time. So you will be getting the time. The time would be 8.86 hours. So if he plays both games together simultaneously, he will lose like $990 in 8 hours, 8.86 hours. So this is an application of a parallel reaction. Any questions so far? Okay, Nan. So we will proceed. If there's no more question, we go back to our slides. Okay, so that would be for our parallel reaction. So let's go to homogeneous catalyzed reactions. Homogeneous and has the presence of a catalyst. So the reaction rate for this type of reaction is the sum. So take note, it is the sum of the uncatalyzed and catalyzed reaction. So you have to set up two equations, two reactions then. One that is not catalyzed, this one is the uncatalyzed reaction. This one is the catalyzed reaction. You see the presence of the catalyst in both sides of your equation. Since it's not being consumed, then of course it has to appear in both sides of your equation. So this is again the uncatalyzed reaction and the catalyzed reaction. You have to set up also rate expressions for each of these reactions that you have written. So for the uncatalyzed, that would be K1 C sub A. So they are not parallel reactions, but rather you simply set up two reactions. And the second one is for the catalyzed reaction. So instead of only having K sub 2, the rate constant, and the concentration of A, now you have multiplied the two by the concentration of the catalyst. You are to take note that class, the concentration of the catalyst here is a constant, just like the K sub 2. So if we proceed to the next slide, the reaction will proceed even without the catalyst present. So we know that in the case of homogeneous catalyzed reactions, and in most cases, this is the thing that is happening, even if we don't have the presence of the catalyst, the reaction will still happen. So the purpose of the catalyst is just to shorten the time for the reaction to, let's say, produce the corresponding yield that it wants to produce. So the reaction will proceed without the catalyst present, and the rate of the catalyzed reaction is directly proportional to the catalyst concentration. So just like the parallel reactions that we have discussed a while ago, we also set up a net rate equation for both the uncatalyzed and the catalyzed reaction. And again, just like in parallel reaction, we have factored out the C sub A since it's common in here. And we have these constants. All are constants. K sub 1 is a constant. K sub 2 is a constant, just like C sub C is a constant. If you're going to separate variables for this differential equation, this will be your answer. This one, the CA over CAO is 1 minus XA. And that would be equated to the product of K1 plus K sub 2, C sub C, all of which is multiplied to T. Now, Levenspiel like to call this one the combination of the K's and the C sub C as the K observed. So it's the K observed times the T then on the right side of our equation. Now, making a series of runs at different catalyst concentration will help us solve for the two rate constants. So if you look at this particular equation class, if you have different catalyst concentration, different catalyst concentrations, you'll be able to find the K sub 1 and the K sub 2 value. So making a series of runs at different catalyst concentrations allows you to determine K sub 1 and K sub 2. How is that? So that would be presented later with an example. This is accomplished. So this one explains the previous concept here. So this is accomplished by plotting the K observed or the given rate constant for your homogeneous catalyzed reaction against the catalyst concentration. The plot will give you the intercept, which is equal to K1, and the slope, which is equal to K2. Now, for that to be understood, let's say, for example, we'll write here what this thing represents. Remember that Levenspiel represented K sub O as K sub 1 plus K sub 2 C sub C. Okay? So what happens here, you are to plot this against this. The plot will give you a slope, which is K sub 2, and a y-intercept, which is K sub 1. So you are going to plot what? You're going to plot your given rate constant, the given rate constant versus the catalyst concentration. The given rate constant, so meaning class, the problem for a homogeneous catalyzed reaction will give you the K sub O, or simply the K for that matter, the rate constant for that particular reaction, and the different catalyst concentrations that were used. So different catalyst concentrations here and the corresponding rate constants of your reaction based on these different catalyst concentrations. So if you plot the two, then you will have the slope and the y-intercept for the K sub 2 and the K sub 1 respectively. That's how you now know. That's how you know rather. So if you go back to this particular slide here. So knowing K sub 1 would help you compare how will the rate of this reaction compare with this. So you will have K sub 1 for the rate constant for the uncatalyzed reaction and K sub 2 for the catalyzed reaction. So we are expecting, of course, that K sub 2 has to be greater than K sub 1 because this one is already your catalyzed reaction. So again, remember that you are given here the initial, or rather you're given the catalyst concentration and the rate constants. Okay, catalyst concentration with the rate constants, that will help you find the two rate constants. Okay, now let me see if I still have. Now, we'll have a problem from Levenspiel that will illustrate the use of this particular concept. Okay, so it should be homogeneous catalyzed reaction. Okay, so here we are. 3.24. In the presence of a homogeneous catalyst of given concentration, aqueous reactant A is converted to product at the following rates and concentration. The following rates, and Ca alone rather determines this rate. So this time you're given the concentration of A and the corresponding rate of reaction. So you're not given here the catalyst concentration, but rather you're given the rate of reaction. We plan to run this reaction in a batch reactor at the same catalyst concentration as used in getting the above data. So meaning whatever is the catalyst concentration used here, that would be the same catalyst concentration that will be used again. Find the time needed to lower the concentration of A from an initial concentration of 10 moles per liter to 2 moles per liter. So take note that this is a homogeneous catalyzed reaction because it has the presence of a catalyst. Okay, A is being converted in this sense. So there was no mention of any substance other than A. So then A must be the only species that is present in your reaction. So let's write down the given for this particular problem. So this is 3.24. So this problem is talking about a homogeneous catalyzed reaction. And you're provided with the data, but the data that was provided is having to start with having the rate values below what would be the remaining concentration of A, given the rates below. So this one has the unit liter, a mole per liter per hour. This one must be then mole per liter. Okay, so this would be the set of units for our quantity. So you have 1, 2, 4, 6, 7, 9, 12. And you have 0.06 for the 1. This is 0.1. This is 0.25. This is 1.0. This is 2.0. This is another 1.0. And this is 0.5. So there's no trend actually here because from 1, it went up to 2, then went down to 1. In here, it's increasing, then it's decreasing here, then increased again. So there's no trend. This is the set of information that's provided. And you are required to find the time when CaO equal to 10 moles per liter is converted to Ca, which is 2 moles per liter. Okay, so we have to start solving this problem with, of course, how would we write the net rate equation for a, shall we say, a homogeneous catalyzed reaction. So if you recall the slide, so the rate of reaction of A is equal to K sub 1 plus K sub 2, C sub C times C sub A. And this is K sub O, K observed, as the way it's labeled or called for by the author of the book where this problem came from. So what we're going to do in here, if you're going to look very closely, class, excuse me, and if you're going to use the linearization process, you can take ln of both sides, ln of RA excuse me, ln of CO plus ln of CA. Coming from the fact that you will have here ln of the product of KO and C sub A. If we have product, that would be equivalent to, shall we say, splitting both of the, shall we say, parameters here as arguments of the ln. However, if we do that, there isn't anything that's left here. Whereas we have ln KO here, which could be our y-intercept. I'm just presenting this to you. And this is a 1, understood to be a 1, right? This one could be your x, and this could be your y. But we're not certain that your slope here, the number that you'll be getting here, will be equal to 1 in this case. But nonetheless, whatever is the number that you're getting here, that would be the slope of this particular line. And the K sub O, which is the y-intercept, will give you the K observed, this one. So the y-intercept, what did I say? The y-intercept here will give you the K sub O, which will point out to you the K observed. So that could be one option that you can do, or you can do a simple averaging. So for the K sub O, you solve for the K sub O using this one pair of data, another pair of data, then average anything. But this one would be a lot, how shall I say, this would be more accurate. Now, as an exercise, can you please do that? So what we're going to do now, I'll have here another sheet. So your raw data, which I placed in there, should be now changed to, you have here ln-CA and ln of the rate. So the data that I have written here, you have to take the ln of, and you will use linear regression in finding the ln K sub O. So you get ln of CA and ln of the rate. So for here, this one, the ln of CA for this part is ln of 1, that would be 0. The ln here that we want is the ln of 0.06. Can you get, please, the ln of 0.06 in here? What's the ln of 0.06?
Negative 2.8134, Miss.
Okay. Then next would be the ln of 2. Ln of 2.
0.6931, Miss.
Again.
0.6931.
Thank you. Then we have here ln of 0.1.
Negative 2.30, negative 2.30, Miss.
30. Thank you. Then we have ln of 4.
1.39.
Okay, ln of 0.25. Negative.
1.39, Miss.
Okay, then we have ln of 6.
1.7917.
17. And ln of, here we have ln of 1, so this is a 0. Then ln of 7.
1.95.
1.95. Then ln of 2.
Ln of 2, Miss, 0.693.
0.693. Okay, may 2 na tugali sa babaw. Then we have here, what's next? 9. ln of 9.
2.197.
Iba naman yun, si Sarah lang tanan. ln of 1 is 0. Then ln of 12.
2.48, Miss.
Thank you. Then last is ln of 0.5, negative
0.693.
0.693. Okay.
Yes, Miss.
Okay, thank you. So this would be your y, and this would be your x. Now, whatever is the y-intercept when you do linear regression, that's equivalent to ln of k sub o. Can you please get the best fit line equation for this one and provide me with the b? With the b, because we need the k sub o.
Negative negative 2.8219.
Again, negative 2.8219.
8219.
So that would be our ln of k sub o. Kindly solve for k sub o. Raise everything to e. E raised to negative 2.8219 is
0.5948.
0.5948. Thank you. Okay, so that would be our k sub o. Now we go back to our rate. And this is how we represent it. The rate of change of concentration of A with respect to time. And that's equivalent to K sub O CA. Okay, remember this K sub O is K1 plus K sub 2 C sub C. Now we have it here already. So then you will just do separation of variables. And you have K sub O dt. And you'll have here ln of CA over CAO being equal to the 0.5948 and the time. So if we substitute, I'll write it here, the substitute provided in the problem that we want to determine the time for an initial concentration of 10 to lower down to 2, how long would that be? Okay, so the time is negative ln of 0.2 divided by 0.5948. Anyone? Are you still there?
2.71 is naka miss.
2.71 hours. Okay, sige. Okay. The reason why I had you do this, it's because I had it solved using the averaging. What do I mean with the averaging? So actually, this is really the answer. You have to do linearization in this case. So that would be T being equal to 2.79 hours. If you did not do that, and what you did was something like this, go to the next. If you did some,
Miss,
yes.
excuse miss. Sa kagina bala miss sa KO bala miss. Di ba
Oo.
miss? Hindi siya guro miss 0.5948 dapat guro 0.059.
I, sige, did not get it correctly. This one,
Hindi miss sa next na miss.
next where?
Ang kagina bala miss nga na-solve na ang ln of KO.
Na-solve na ang ln of KO. Ini?
Oo
Ini.
miss.
Oo. Si amo na yung ginhatag sa akon. This was the y in,
Ng ano miss, ln of, a negative ln of 2/10 equals 0.059.
Ang gimme niya miss pagkuha sa time is
Oo, miss ang time.
dali na yun. LNCA over CEO.
this is 2, this is 10.
Then equals dapat
Equals dapat miss sa 0.059.
Hindi siya, 0.59. Maging divide pa siya sa 10.
Ang sa KO, miss, kaya nakulang lang
Oo,
kaginan
miss.
zero ang sa zero.
Amo na, oo. Amo na
Oo,
gani,
miss.
kaya nakulang siya. Okay, so I also naintindihan ko, magaling wala siya ma-reflect. So pila na siya?
27.1, miss.
Okay. So madako siya. 27.1. Okay, so I added this one, so this should be changed. Correspondingly, this will change also. So this is the time that you'll be getting if you have done linearization. As I was saying, so what if you did not do linearization, like you treated the raw data, this raw data in here, like to use a different. And what I did with the raw data is just, for example, this is my first set of raw data. I dealt with it like this. RA is equal to K sub O CA. So directly, I will place here 0.06 and I will have K sub O. Let's say I will have this as K sub O1 because that's for my first set of data. And the CA value that I will place here is 1. So I will have a KO1 which is equal to 0.06. I will do the same for this, and all of this in here. And average. If you do that, the answer is really very far because the K average of these KOs for each of this pair of data would be 0.11111, which is very far from this value that we got if we use centralization. So that's the purpose that you need not average the values that are given because they are not, shall I say, it's not a straight line, but rather, as you can see with the data, it's even from 1 to 2 to 1 again to 0.5. I'm referring to the rates. So there's no clear pattern as to the behavior of the rate with respect to the remaining concentration. So don't average data whenever you're provided experimental data, but rather use linearization whenever possible. In this case, you can use linearization, so do that. Anyway, your calculators can process that for you. So this should be really, by the way, this is per hour. So this should be your, this is really your appropriate K sub O or K observed already consisting of the sum of K sub 1 and K sub 2 C sub C. Not the average one when you treat the pair of data individually, crudely like this, and then simply average all the case. So that's how we use the concept of the homogeneous catalyzed reaction in processing problems related to it. So for now, we'll be having a 5-minute break and then we transfer to the other link that I gave you because I might be checked there by the checker as well. So I will stop recording here for now and stop sharing. And I will end here. We use the second link.